Okay, let me point out that did these calculations, and you would have gotten the same thing had you done the calculations, that if your y factor is 1.6, p is about 0.68, which is pretty close to 2/3. Hopefully you recognize that immediately. A y factor of 1.8 would give us a p of 0.85. A y factor of 1.4 would give us a p close to 0.5, and so would a y factor of 1.5. So what we're seeing is this part of the curve predicts a y factor of about 0.85, getting fairly close to 1, meaning the graph would be a straight line or linear if p was 1. And a factor of about 0.5 if we use this part of the graph. Notice that there's kind of an anomaly again in the way I drew the graph. It's probably too steep from here to here, and probably doesn't quite have the right shape. So if you believe this part of the graph more than this part of the graph, you would go with the smaller y factor and the smaller value of p. If you believe this part of the graph more, you would go with a larger value of p. So I'm going to go with the in-between value of p. 2/3 seems plausible if we don't think through, if we don't know the physics of what's going on, and maybe if we do know the physics of what's going on, this is exactly what we get. It's possible. And any of these others is possible. It's okay, we don't know. We don't know. That's not what's important right now. The process is what we want. So what we're given then is, I'm going to use p equals 0.68, so I'm going to have 0.68 for my power. So p equals 0.68, x would equal what? Well, it's 1 foot. Now I'm not going to use the units right now. We're just going to understand that x is in feet and y is going to be in counts per minute, or cycles per minute if you prefer, which is actually more standard. And okay, I wrote 1 and 52, and I needed to write x equals 1 and y equals 52. So let me see if I can correct that. Okay. So my model is, we don't know what A is yet, although we kind of do. You can pretty much see that if you've already worked it through, but I'm going to write it down in detail because this is what you have to do and what we're going to have to do in the next question I'm going to ask you. Okay, so 52 equals A times 1 to the 0.68. And let's make the one a little fancier. I'm making it fancier, I kind of messed it up. So A equals 1, and now our model is y equals 52x to the 0.68. Now, if you got y factors closer to 1.4 or 1.5, then you would probably say x to something close to the 0.5 power rather than the 0.68. And we could also say, and you would still get the 52 because you still have just one unit of x here. So this would be just looking forward. Okay, so we could say that using F for frequency and L for length, so I'll use F for frequency, capital L for length, could it be that this 0.68 really represents a 2/3 power? And if you use a number closer to 0.5, could it really be that it's L to the 0.5 or the 1/2 power, meaning, of course, the square root of x. The 2/3 power would be the square root of the cube of L, the cube root of the square of L. Okay? Okay, well, that's what we would get depending on how you estimated this power, and you might have used some other power. You know, if you're close to 6, 0.6, then you might say, is it the 3/5 power maybe? At this point, we're just shooting in the dark. We don't really know what the power should be. We don't know what the ideal model is, and we're just looking at our data and obtaining a model based only on the data.